Welcome back, design junkies, to Mechanical Engineering Made Simple. If the podcast brings you value, help support the show with a like, a follow, or leave a comment below. Imagine for a second that you are staring at a massively expensive jet engine. I mean, it was flawlessly designed in CAD, you know. The mathematical model said it was perfectly safe.
Right, the materials were pristine when they rolled off the assembly line.
Exactly. But then suddenly, at 30,000 feet, a critical shaft it snaps in half and the engine rips itself apart? Like, why did it fail?
Yeah, how does a design that works perfectly on a computer screen become an absolute disaster in the real world?
So today, we are taking a massive deep dive into the most foundational yet complex questions that you, the engineer, ask about mechanical design, stress, materials, and mathematical optimization.
Because the gap between a digital model and physical reality, well, that's where the true art of engineering lives. I mean, we have a mountain of data today.
Oh, for sure. Textbooks full of stress analysis algorithms.
Yeah, and vast libraries of material science data. Plus, structural optimization software that runs like millions of calculations a second.
But looking up a yield strength number in a handbook, that doesn't make you a great designer.
No, it really doesn't. The true skill is connecting the dots. It's understanding the fundamental micromechanics of how a part fails,
Right.
how the specific crystalline structure resists that failure, and how we mathematically optimize the geometry so it survives without overbuilding it into some massive heavy block of metal.
Okay, let's unpack this, because the reality of engineering is that designing a part is, well, it's relatively easy. Drawing a beautiful 3D model on your computer is easy.
Oh, yeah. Anyone can make something look good in CAD.
But designing a part that actually survives the chaotic, unpredictable real world, that is an entirely different beast.
It really is. I mean, you might think you've designed the perfect rotating shaft for an industrial motor.
But before we can even begin to talk about things breaking, we have to understand the invisible mathematical forces acting upon them. We can't see stress, right? We can't see strain.
Exactly, we have to model it, which raises a huge question for anyone designing rotating machinery. How do we accurately quantify the twisting and bending forces tearing at our designs?
Yeah, like how do we put a number on that?
Well, to quantify it, we really have to visualize the microscopic reality of the material.
Hmm.
Let's look at the anatomy of stress, specifically torsional stress in circular shafts.
Okay, so twisting a metal bar.
Right. When you hold a metal bar fast at one end and apply a twisting force, a torque to the other, you aren't just stretching the metal. Every single infinitesimally thin circular cross-section of that bar is actively trying to slide over the one next to it.
It's trying to shear off.
Exactly. Imagine a stack of thousands of thin metal coins glued together.
Oh, that's a good way to picture it.
Right. So when you twist the stack, the glue between every single coin is being pushed to its limit as each crane tries to rotate past its neighbor.
And if you were to draw a perfectly straight line down the side of that shaft with a marker before you twisted it, that line wouldn't just stretch.
No, it would wrap around the cylinder and become a continuous helix. The angle of that twist accumulates over the length of the bar.
And here is the critical part for you as a designer. The shearing stress at any given point inside that material is directly proportional to its radial distance from the central axis.
Right, which means the material at the dead center of the shaft, the neutral axis, isn't moving relative to itself. It's experiencing essentially zero torsional stress.
Wow, zero stress at the center. But the material at the absolute outer surface, like the skin of the shaft, that's taking the maximum beating.
Absolutely. It is being stretched and sheared to its absolute limit. And that physical reality drives one of the most fundamental geometry choices in mechanical engineering.
You're talking about the solid versus the hollow shaft, right?
Yep. Because the material in the center of a solid shaft is experiencing zero stress. It's doing practically zero work to resist the twisting moment.
It's just dead weight.
Exactly. It's essentially dead weight. Yeah. And if you are designing for aerospace or automotive or anywhere weight matters, that dead weight is unacceptable.
So hollow shafts are vastly more efficient in torsion, then.
Ooh, incredibly so. By removing the inner core and pushing that same mass of material out to a larger outer diameter, you drastically increase what we call the polar moment of inertia.
So you're putting the metal exactly where the stress is highest.
Exactly. You put it where it's needed most.
Which is exactly why biological structures evolved this way. I mean, look at bird bones or human femurs, or even engineered structures like the massive drive shafts underneath semi-trucks.
Right. They are all hollow tubes. They maximize torsional stiffness while shedding pounds.
But, as an engineer, I can't just say, make it hollow, I need a hard number. How do we actually calculate that outer maximum stress?
Well, there is a very specific mathematical relationship engineers rely on when sizing shafts for transmitting power.
Okay, let's hear the math.
When a solid round shaft is transmitting power from a motor to a load, we can calculate that maximum unit shearing stress directly.
Right.
The formula states that tau equals 321,000 times h divided by the product of n and d cubed.
Okay, so tau equals 321,000 times h divided by the product of n and d cubed. What do those variables mean in the real world?
So tau represents the maximum shear stress. H is the horsepower being transmitted by the system. N is the rotational speed in revolutions per minute, and d is the diameter of the shaft.
Got it. So it's an inverse cubic relationship with the diameter. If I make the shaft just a tiny bit wider, the stress drops massively because of that d cubed term in the denominator.
Exactly. The diameter has a massive impact. So
Yeah.
you plug in your motor's horsepower, you plug in the RPM, and you immediately know the exact shear stress trying to rip the outer skin of your shaft apart.
But there's a massive catch here, isn't there? I mean, in the real world, a pure, isolated state of torsion almost never exists.
It is incredibly rare. Real parts in real machines experience complex combined stresses. Think about that rotating motor shaft again.
Right. It's not just floating in space.
Exactly. It isn't twisting freely in a vacuum. Maybe there's a heavy drive pulley mounted on the end of it, pulling down with hundreds of pounds of belt tension.
Or maybe there's a helical gear meshing with another gear, pushing radially and axially against the shaft.
Yep, that means the shaft is bending, so it's experiencing longitudinal tension and compression. At the exact same time, it is experiencing torsional shear.
And these forces don't politely take turns. They stack right on top of each other.
They absolutely do. The longitudinal normal stresses from bending interact continuously with the shearing stresses from torsion. As a designer, you have to figure out the worst-case scenario happening inside that three-dimensional stress state.
And this is where Mohr's circle becomes an absolutely vital, non-negotiable tool, doesn't it?
Oh, 100%. Mohr's circle is essential here.
You know, Mohr's circle was always one of those things that looked completely terrifying on a chalkboard in engineering school.
Oh, I know. It scares a lot of students.
But conceptually, I like to think of Mohr's circle like a camera. Imagine a camera orbiting around a microscopic three-dimensional cube of metal hidden deep inside the shaft.
That's a really great way to visualize it.
Right. And as that imaginary camera changes its viewing angle, rotating around the cube, the mix of pulling forces and sliding forces changes on the screen.
Exactly.
Mohr's circle is essentially just a graphical and mathematical method of finding the exact camera angle where the pulling force, the normal stress, looks the absolute biggest, and the sliding force, the shear stress, completely disappears.
And we call those the principal planes and the principal stresses. That orbital camera analogy perfectly captures the mathematics of coordinate transformation.
So you're just hunting for the worst possible angle.
Exactly. You are rotating your frame of reference until you find the plane of maximum normal stress, or, conversely, the plane of maximum shear stress.
Because the material doesn't care what arbitrary XYZ coordinate system you drew in your CAD program.
Right. The material only feels the maximum principal stress acting on its internal crystal lattice.
So if a shaft is simultaneously twisting and bending, how does the metal actually know when to yield? Like, how does it know when the combination of these forces is just too much?
Well, that's where failure theories come in.
I always think of the analogy of wringing out a wet towel. If you take a wet towel and just pull it straight from both ends, pure tension, it takes an immense amount of force to actually rip the fabric.
It does. It's surprisingly strong in pure tension.
But if you wring it out, twisting it tightly while simultaneously pulling it from both ends, you are combining severe shear with tension. The fibers of the towel are going to snap much, much sooner than they would in pure tension alone.
That's right.
The towel knows to yield because those combined stresses amplify each other on specific microscopic planes.
The towel analogy hits on the exact reason engineers have spent over a century developing specific failure theories. We need to predict exactly when that towel will snap based on its specific material properties.
And different materials act completely differently, right?
Yes, the crucial realization is that different materials know they are failing in fundamentally different ways. We really have to contrast the criteria we use for brittle materials versus ductile materials.
Okay, let's start with brittle materials, like cast iron, glass, ceramics, or even concrete.
For those, we rely on the maximum stress theory, which is historically called Rankine's theory.
Rankine's theory, what does that assume?
This theory assumes that a brittle material will fail the exact moment the maximum principal tensile stress reaches the ultimate tensile strength of the material.
So it completely ignores the other axes.
Exactly. It operates completely regardless of what the shear stresses or the compressive stresses are doing on the other axis. Brittle materials don't flow. They fail by sudden catastrophic cleavage. The atomic bonds simply pull apart.
Like snapping a piece of blackboard chalk in your hands. There's no warning, no stretching, just a sudden pop, and it's in two pieces.
Precisely the behavior. But if you are designing with ductile materials, like structural steel, aluminum, or brass strip, they behave completely differently.
They yield, right? They bend before they break.
Yes. They deform plastically and permanently before they ever reach their breaking point. For ductile metals, we use the distortion energy theory.
Ah, the famous von Mises criterion. Every mechanical engineer knows that name.
Yep, von Mises. And this theory is much more sophisticated. It states that yielding begins when the distortion strain energy per unit volume reaches the distortion strain energy at yield in simple tension.
Okay, let's break that down, because distortion strain energy is a pretty heavy term. What is actually happening to the metal physically?
Think of it this way. Any complex stress state can be broken down into two components. First, there is hydrostatic stress, which is uniform pressure from all sides.
Like dropping a block of steel to the bottom of the Mariana Trench?
Exactly. It experiences immense hydrostatic pressure. It will shrink slightly in volume, but it won't yield or change its overall shape because the pressure is equal everywhere.
Okay, so that's hydrostatic. What's the second component?
The second component is deviatoric stress, or distortion stress. This is the stress that actually tries to change the shape of the cube, stretching it into a rectangle or skewing it into a parallelogram.
Oh, I see. So it's the shape-changing force.
Right. The von Mises criterion calculates the energy of just that shape-changing distortion. It takes all your complex 3D stresses, strips away the harmless hydrostatic pressure, and calculates a single equivalent stress.
And then you just compare the equivalent von Mises stress to the standard yield strength you looked up in your textbook.
Exactly. It is an incredibly accurate predictor for how the crystalline lattice of a ductile metal decides to slip and flow.
Okay, so we've done the math. We've calculated the static stresses using the torque and bending loads. We rotated our camera with Mohr's circle. We calculated the von Mises equivalent stress, checked our material properties, and the math says the part should theoretically survive with a massive factor of safety.
Right. The math checks out perfectly.
We build it, we turn the machine on, it runs flawlessly. So why does that exact same shaft suddenly snap in half after a year of use under loads we know are completely safe and well below the yield strength?
Well, that question transitions us out of the comforting, predictable world of static loading, and it drops us straight into the chaotic, dynamic world of fatigue and fracture.
Ah, fatigue, the silent killer.
Exactly. What you are describing is a progressive failure phenomenon. Fatigue happens when a material is subjected to cyclic loading forces that fluctuate, reverse, or pulse over time.
So it's the repetition that kills it.
Right. The insidious nature of fatigue is that even if your peak operating stress is vastly below the von Mises yield strength of the material, the repeated thousands upon thousands of applications of that low stress can initiate highly localized microscopic damage.
So like a tiny slip band forms on the surface.
Yep, which turns into a microcrack, which slowly grows with every single revolution of the motor until the remaining cross-section of the shaft is too small to carry the load and it just snaps.
The classic example of this is bending a paperclip, right?
Yeah.
You can't pull a paperclip apart with your bare hands. It's too strong in static tension.
No, you'd cut your fingers before it broke in pure tension.
But if you bend it back and forth a dozen times, it easily snaps. We generally divide this fatigue behavior into two main regimes, right? High cycle fatigue and low cycle fatigue.
We do, and the distinction is vital for how we design. High cycle fatigue involves relatively low fluctuating loads, where the global strain in the material remains almost entirely elastic.
So the part springs back to its original shape every single time.
Exactly. Because the plastic damage per cycle is infinitesimally small, maybe localized to a few grains of metal at a surface scratch, it typically takes a massive number of cycles to cause failure.
Like how massive are we talking?
Usually defined as greater than 10,000 cycles, but often stretching into the millions or billions for things like engine valves.
Wow, billions of cycles. And low cycle fatigue is the opposite.
Right. Low cycle fatigue involves massive loads that push significant portions of the material into the plastic strain range on every single cycle.
So it's permanently deforming a little bit every time.
Yeah. The damage accumulates brutally fast, leading to catastrophic failure in fewer than 10,000 cycles.
Here's where it gets really interesting, because if we look at the real world, a part isn't just sitting in a laboratory testing machine experiencing a single, perfect, constant sine wave of repeating load.
No, real-world loads are a mess.
Think about the suspension control arm on your car. You back out of your driveway, which is a small load, then you drive on a perfectly smooth highway for an hour, accumulating thousands of tiny stress cycles.
Right.
Then you hit a massive pothole, which is a huge stress spike. Then you drive on a violently corrugated gravel road. The stress spectrum is complete chaos. How on earth do you account for a history of varying loads?
That is one of the most difficult challenges in mechanical design, honestly. And we handle it using cumulative damage theories.
Okay, cumulative damage, what's the main theory there?
The most famous and widely utilized is the Palmgren-Minor linear damage rule. It is a brilliant, highly intuitive concept. It postulates that every single stress cycle, no matter how small, consumes a specific fraction of the material's total fatigue life.
I have always thought of the Palmgren-Minor rule like a bucket of structural health.
Oh, that's a good analogy.
Yeah, when the part rolls off the assembly line, the bucket is completely full of water. And every time you apply a load cycle, you scoop a little water out.
Exactly the right visualization. If you look at an SN curve, a graph of stress versus number of cycles to failure, you might see that at a specific high stress level, the part will fail in exactly 100,000 cycles. If you drive over that corrugated gravel road and subject the suspension to 10,000 cycles at that high stress, you have scooped out 10% of the water. You have consumed 10% of the part's life.
And Minor's rule just lets you add those up.
Yes. Minor's rule allows you to linearly add up these damage fractions from completely different load spectrums, the driveway, the highway, the pothole.
Yeah.
You calculate the ratio of cycles applied divided by cycles to failure at every stress level.
So when the sum of those fractions reaches 1.0 or 100%, the bucket is empty and the math predicts failure.
You've got it. But there is an issue with the Palmgren-Minor rule.
What's that?
Well, it and SN curves in general are fundamentally assuming we're starting with a perfect part. They track the initiation of a crack and its eventual failure.
Ah, right.
Yep.
But let's be totally honest about manufacturing. Perfect materials do not exist. There are inherent flaws in everything.
Absolutely everything.
There are micro-inclusions of slag from the casting process, microscopic scratches from the lathe cutting tool, tiny voids from welding. What if the crack is already there on day one?
That realization that nothing is perfect forms the entire basis of fracture mechanics. It represents a massive philosophical shift in engineering.
How so?
We stop asking the traditional question of when will a crack form, and we just accept reality. We assume flaws already exist.
So what's a new question then?
The new questions become, how fast will this existing flaw grow under my cyclic loads, and at what exact length will it cause a sudden explosive fracture?
So we abandon simple stress calculations entirely.
Pretty much. We compare two highly specific key parameters instead, the stress intensity factor and the fracture toughness.
Okay, let's define those, because they sound similar, but they do very different things, right?
Very different. The stress intensity factor, denoted by the letter K, characterizes the strength of the stress field acting right into the unimaginably sharp tip of the crack.
So it's an applied condition.
Yes. It depends on the global load you are applying to the part, the geometry of the part, and critically, the current length of the crack.
And what about fracture toughness?
Fracture toughness, on the other hand, is a fundamental inherent property of the material itself, just like density or melting point. It is the critical maximum value of that stress intensity factor that the atomic lattice can actually withstand.
So if your applied stress intensity factor reaches the material's fracture toughness, the crack abruptly becomes unstable.
Exactly. It stops growing slowly and propagates at nearly the speed of sound, shattering the part instantly.
And to track how that crack grows over time, cycle by cycle, creeping closer to that critical fracture toughness, engineers use a mathematical relationship called the Paris law.
Yes, the Paris law is crucial here.
Using spoken math, the Paris law states the derivative of A with respect to n equals c multiplied by the quantity delta k raised to the nth power. Let's translate that into physical reality.
Sure. So A is the length of the crack, N is the number of fatigue cycles.
So dat n is simply the rate of crack growth per cycle.
Right. Delta K is the range of the stress intensity factor during that cycle, and C and N are constants specific to the metal you're using.
What the Paris law reveals is honestly terrifying for longevity. It tells us that crack growth is not linear, it's exponential.
It absolutely is, because the stress intensity factor depends on the crack length. As the crack gets just a tiny bit longer today, the stress concentration at its tip increases.
That acts like a magnifying glass, focusing the load tighter and tighter.
Exactly. Which means tomorrow, the crack grows faster than it did today, and the day after that, it grows even faster. The Paris law models an accelerating death spiral for the component.
But there is a limit to the math, right? I mean, the Paris law and linear elastic fracture mechanics work beautifully on brittle materials, or when the crack is really small.
They do.
But they assume the material right at the incredibly sharp tip of the crack is behaving elastically. In ductile metals, that just isn't true. The stress gets so insanely high at that microscopic point that the metal yields.
Right, a tiny bubble of plastic deformation forms right at the crack tip.
Yes, the crack tip plastic zone. And when that plastic zone gets too large compared to the thickness of the part, the linear math completely breaks down. It gives you dangerously inaccurate predictions.
That is exactly when structural integrity engineers must shift their methodology. We have to use failure assessment diagrams, or FADs.
FADs, how do those work?
A FAD is a highly sophisticated two-dimensional plot that acknowledges a part can fail in two completely different ways simultaneously. It assesses the risk of brittle fracture on the y-axis and plastic collapse, which is gross yielding of the entire remaining cross-section on the x-axis.
So it's plotting both risks at once.
Yes. The diagram has a failure curve drawn on it. You take your operating conditions, your crack size, and your loads, and you plot them as a single coordinate point on this diagram.
And if your point falls safely inside the curve, closer to the origin, the part will hold.
Exactly. But if your point falls outside the curve, the part fails. FADs beautifully bridge the gap between pure fracture mechanics and pure yield mechanics.
I want to circle back to something we touched on earlier with low cycle fatigue. There is a fascinating concept called the transition life.
Yes.
Imagine I'm designing a solid rocket motor casing for a missile. It only has to survive a few hundred massive thermal and pressure cycles before its mission is over and it's discarded.
Right, a very short, extreme life.
Contrast that with a steam turbine in a power plant that has to spin at 60 hertz for 40 years. How does that vastly different required lifespan change my material choice?
That specific dilemma is solved by the Manson-Coffin relationship. This equation mathematically relates the plastic strain amplitude experienced during a cycle to the total fatigue life of the part.
Okay, so if you plot the elastic strain life and the plastic strain life on a log graph, they form two intersecting lines.
Right, and the transition life is the exact intersection point. The number of cycles where the damage from elastic strain and the damage from plastic strain are perfectly equal.
So how does knowing that transition life actually guide the engineer's hand when picking a metal?
It dictates your primary material property requirement. If your design life is vastly shorter than this transition life, like your rocket motor casing, the plastic strain is doing all the damage. It totally dominates the failure mode.
So what do you want in that scenario?
In that scenario, you actually want a material with exceptionally high ductility. You want a metal that can stretch, yield, and absorb that gross plastic deformation cycle after cycle without snapping.
But if your design life is much longer than the transition life, like the steam turbine elastic strain dominates, the part is hardly yielding at all.
Exactly. For that, ductility is less important, and you need a material with an exceptionally high ultimate tensile strength.
It is a classic engineering trade-off, then.
It is. Highly ductile materials are your best defense for short, brutal design lives, while ultra-high-strength materials are required for long, repetitive design lives.
Which perfectly transitions us into our next major topic. We spent all this time talking about fatigue, which is entirely driven by cyclic mechanical loads.
Right, things moving back and forth.
But what about the slow, silent enemies? The enemies of time, temperature, and environment. What happens when the physical operating environment itself turns hostile?
Oh, when the environment turns hostile, we step into the realm of creep, fretting, and corrosion.
The silent destroyers.
Truly. These are the silent destroyers because they don't require sudden impacts or massive loads to ruin a design. Let's start with creep.
Okay, creep, what is it?
Engineers define creep as the time-dependent, permanent plastic deformation of a material subjected to a constant load at elevated temperatures.
This one bends the mind a bit. If I hang a heavy 1,000-pound weight on a steel rod in my garage at room temperature, it stretches elastically by a fraction of a millimeter and stops.
And it will hang there for 1,000 years without stretching another micron.
Right. But if I introduce heat...
Heat changes all the rules of atomic bonding. If you heat that steel rod up to roughly 35 to 70% of its absolute melting temperature, it will continue to stretch.
Really? Just from the heat?
Yes. Very slowly, over thousands of hours, it will elongate, even if that 1,000-pound load never changes. The thermal energy allows the atoms in the crystal lattice to slowly diffuse, sliding past obstacles that would normally stop them at room temperature.
So it's literally flowing, like an incredibly thick, slow-moving liquid.
Exactly. And this flow, this creep, happens in 3 distinct metallurgical stages.
Let's go through them.
First is primary, or transient creep. When the heat is first applied, the deformation rate starts fast, but it gradually slows down because the metal is strain hardening as it stretches.
So the dislocations in the crystal lattice get tangled up.
Yep. Then it enters secondary, or steady-state creep. The rate of stretching becomes completely constant. The strain hardening is perfectly balanced by thermal softening.
And this secondary stage is where the part spends the vast majority of its useful operating life, right?
Yes, it is. But eventually it hits tertiary creep. The internal microstructure of the metal literally begins to break down. Microscopic voids form at the grain boundaries.
Oh, wow. So the remaining cross-section actually shrinks.
Exactly. The strain rate accelerates rapidly, and the part inevitably pulls apart in a catastrophic failure called stress rupture.
That is a terrifying reality for things like jet engine turbine blades. I mean, they are spinning at 20,000 RPM under massive centrifugal loads pulling them outward, sitting directly inside a blazing inferno of combusting jet fuel.
It's the ultimate extreme environment.
They are constantly crouping, growing microscopic fractions of an inch longer every flight until they have to be retired before they strike the engine casing.
Yeah, creep is a massive design factor there.
But heat isn't the only silent destroyer. What about fretting? I think about a bearing press fit onto a shaft or 2 heavy steel plates tightly bolted together.
Right. Typical rigid joints.
The joint is completely clamped down. It isn't supposed to move at all. But under dynamic machine loads, it vibrates microscopically.
And those microscopic vibrations are deadly. We are talking about minute cyclic relative motions, often just a few thousandths of an inch of slip.
And that tiny rubbing causes fretting action.
Exactly. Even machine surfaces look like jagged mountain ranges under a microscope. When those 2 clamped surfaces rub together, they micro-weld and tear off microscopic asperities, the tiny peaks of the metal surface.
And because it's metal tearing, you get debris. But it's worse than just metal dust, right?
Much, much worse. Because those torn-off microscopic particles of fresh metal have massive surface area, they immediately oxidize in the surrounding air.
So they turn into metal oxide, like rust or aluminum oxide.
Right, which is essentially ceramic. It is incredibly hard. This creates a hard, highly abrasive debris that gets completely trapped in the tight joint.
So this debris acts like grinding powder, accelerating the wear exponentially.
It does, but the wear isn't even the real danger. The microgouges left behind on the surface of the metal act as severe stress concentrators.
Ah, leading back to fatigue.
Exactly. This leads directly to fretting fatigue, where a massive crack initiates from this hidden, pulverized, vibrating joint and causes a catastrophic structural failure at a load level vastly below the normal fatigue limit.
So it's mechanical wear creating chemical oxidation, which then creates a highly abrasive powder, which causes more mechanical damage, which initiates a fatigue crack. It's just a vicious cycle.
It really is. It feeds on itself.
Speaking of chemical damage, we have to talk about the entire corrosion spectrum, because a lot of people think corrosion just means a rusty bumper on an old truck.
Rust is just the tip of the iceberg. Direct chemical attack is the simplest, most uniform form of corrosion. The metal just uniformly dissolves, thinning out as it sits in an acid or aggressive fluid.
But as an engineer, the insidious, hidden forms of corrosion are much more dangerous because they are localized. Take crevice corrosion, for example.
Oh, crevice corrosion is awful. It happens in tight, stagnant spaces like the gap under a rivet head, beneath a rubber gasket, or inside a threaded hole.
Right. And the fluid inside that tiny gap gets starved of oxygen compared to the surrounding fluid.
Yes, and this sets up a localized concentration cell. The trapped fluid turns highly acidic and aggressively eats into the metal hidden inside the crevice, while the surface out in the open looks perfectly fine.
And then there's pitting corrosion, which is the absolute bane of pipelines and chemical tanks.
Pitting is terrifying because it is an extremely localized attack that drills deep microscopic holes straight down into the metal. It completely bypasses the surface armor.
A tank can look pristine on the outside, but be perforated by thousands of microscopic pits that compromise its pressure vessel integrity.
Exactly. And we also have to account for galvanic corrosion. This occurs when two completely different metals are electrically connected while sitting in an electrolyte, like seawater, or even just salty road slush.
So like a battery cell.
Precisely. The more chemically active metal acts as an anode and will rapidly sacrificially dissolve itself to protect the more noble cathode metal.
Which is exactly why you don't use stainless steel bolts to hold an aluminum boat hull together in the ocean. The massive aluminum hull will literally dissolve into a white powder around the bolt holes, trying to chemically protect the tiny steel bolt.
Yeah, you see that happen all the time when people mix metals improperly.
But the real nightmare scenario for an engineer isn't just one of these failing, it's when these modes team up.
What's fascinating here is the concept of synergistic failure. When mechanical loads and chemical attacks combine, the destructive result is far, far worse than the sum of its parts.
Give us an example.
Take corrosion fatigue. If you have a part experiencing cyclic fatigue loads in a vacuum, it lasts a certain amount of time. If you put it in salt water with no load, it corrodes slowly.
Okay, so isolated, they are predictable.
Right. But if you apply fatigue loads while it's in a corrosive environment, it will fail incredibly fast.
Why does it happen so much faster?
Because of the protective oxide layer. Most metals protect themselves by instantly forming a microscopically thin layer of oxide that seals the surface.
Like a natural shield.
Exactly. But under cyclic fatigue, the metal strains and stretches. That brittle oxide layer cracks, bearing fresh, unprotected, highly reactive metal to the corrosive fluid.
And then the fluid attacks that tiny spot.
Right. The fluid aggressively eats a microscopic pit into that fresh metal. That new pit acts as a stress concentrator, which accelerates the mechanical fatigue crack, which stretches the metal further, breaking more oxide, bearing more metal.
It's a feedback loop, and the exact same mechanism happens in corrosion wear, right?
Yes. Mechanical sliding physically scrapes off the protective oxide layer, accelerating the chemical attack exponentially. The chemical and mechanical forces act as a feedback loop of destruction.
Okay, so we understand the physics of twisting and bending. We understand how fatigue cracks grow. We know exactly how the environment, the temperatures, and the corrosive fluids are going to mercilessly attack our design.
We know what we're up against.
Armed with all that knowledge, how do we choose our armor? When do I look at my CAD screen and say, this bracket needs to be aluminum, or this linkage must be titanium, or break out the nickel superalloys for this turbine?
That decision process is the absolute crux of material selection. Let's look at aluminum first, because it is the undisputed workhorse of lightweight structural design.
How are the different types organized?
The aluminum alloy designation system uses a 4-digit number from the 1000s to the 9000s to categorize them by their primary alloying elements.
So, for example, the 2000s use copper, the 5000s use magnesium, and the 7000s use zinc for aerospace-grade strength.
Exactly. Then you append the tempers. O means fully annealed and dead soft. H means it was strain-hardened by cold working, and T means it was thermally treated, or age-hardened, to lock the crystal structure in a high-strength state.
And aluminum's real superpowers are its manufacturing agility. It's incredibly easy to machine, extrude, and form, and its strength-to-weight ratio.
It's very easy to work with.
But the physical property that always blows my mind is its cryogenic performance. Most metals, particularly standard body-centered cubic carbon steel, have a ductile to brittle transition temperature.
Right, they get brittle in the cold.
You take standard steel, freeze it in liquid nitrogen, hit it with a hammer, and it doesn't dent. It shatters like a glass window. Which, historically, is exactly what happened to the low-grade steel hull of the Titanic in the freezing Atlantic waters.
Yes, a classic example of low-temperature embrittlement.
But aluminum, it actually gets tougher and stronger in extreme cold.
It does, and that is entirely due to its crystalline architecture. Aluminum has a face-centered cubic crystal structure. Because of how closely packed those atoms are, it does not suffer from cold embrittlement.
So it retains its ductility all the way down to absolute zero.
Exactly. That makes aluminum the undisputed king for cryogenic engineering. It is the material of choice for the massive fuel tanks on the space shuttle and modern rockets holding liquid oxygen and liquid hydrogen at hundreds of degrees below zero.
But aluminum has an Achilles heel. When you need high strength at elevated temperatures, it completely fails you. It starts losing its structural strength rapidly as you cross 200 degrees
Yeah,
Celsius.
it gets too soft.
You can't use it near an engine exhaust or in high-speed aerodynamic friction. That is where titanium's aerospace dominance begins.
Titanium is honestly a miracle metal. It is roughly 40% lighter than steel, but can be alloyed to be just as strong. It is incredibly corrosion resistant.
But to use it correctly, you really have to understand its crystallographic phases, right?
Yes, at room temperature, pure titanium exists in the alpha phase, which has a hexagonal close-packed crystal structure. But if you heat it up past roughly 880 degrees Celsius, the crystal lattice completely reshuffles itself into the beta phase.
Which is body-centered cubic.
Right. And by adding specific alloying elements, metallurgists can stabilize these phases at room temperature, creating alpha alloys, beta alloys, and the highly desirable alpha-beta mixed structures.
And the absolute undisputed king of the titanium world is Ti6Al4V, right? 6% aluminum, 4% vanadium. It's an alpha-beta alloy.
It is the apex predator of alloys. It accounts for more than half of all titanium used globally.
Why is it so popular?
The aluminum acts to stabilize the alpha phase, while the vanadium stabilizes the beta phase. This creates a microscopic, interlocking, brick-like structure that gives it phenomenal high strength, excellent fatigue resistance, and allows it to be heat-treated for even more performance.
It forms the backbone of modern military fighter jets, commercial aircraft landing gear, and high-performance medical implants.
It's everywhere in high-end aerospace.
So the obvious question is, why don't we just use titanium for absolutely everything? If it's as strong as steel but nearly half the weight and doesn't rust, why are our cars, bridges, and skyscrapers still made of steel?
The primary barriers are astronomical costs and fabrication difficulties. Extracting titanium from its naturally occurring rutile ore using the corrode process is an incredibly complex, multi-day, energy-intensive process.
It requires chlorine gas and a vacuum environment. Right?
Yep. Furthermore, machining a block of titanium is a machinist's worst nightmare. Because it conducts heat poorly, the extreme heat of cutting doesn't flow into the metal chips, it stays right at the cutting tool.
So the tool overheats.
Badly. The titanium reacts chemically with the carbide cutting tools at high temperatures, galling, smearing, and literally welding itself to the drill bits, snapping them instantly.
Wow. And while it handles heat vastly better than aluminum, titanium isn't invincible. It hits a very strict metallurgical temperature limit around 550 degrees Celsius.
Yes, above that threshold, it rapidly absorbs oxygen and nitrogen directly from the surrounding air, dissolving them into its crystal lattice.
And what happens then?
It becomes hopelessly brittle, forming a hard alpha case that completely ruins its structural integrity.
So when temperatures exceed 550 degrees Celsius, like deep inside the combustion chamber of a gas turbine engine, where the metal is literally glowing white hot, what do? We can't use aluminum, we can't use titanium, steel would just melt.
That is when we call in the heavy artillery, the nickel superalloys. Materials like Inconel 600, waspalloy, and the Mohr family.
The really exotic stuff.
Oh yeah. These alloys are specifically, almost magically engineered to maintain massive tensile strength and resist creep deformation at temperatures where standard steel would be a soft, glowing, useless puddle.
How do they survive that inferno without creeping apart?
They achieve this through complex precipitation hardening. They are alloyed heavily with elements like aluminum and titanium to form microscopic, perfectly ordered, intermetallic precipitates known as gamma prime phases.
Gamma prime phases, what do those do?
They act like millions of tiny concrete roadblocks inside the nickel crystal lattice, physically stopping the dislocations from sliding under high heat.
That's incredible.
Furthermore, by heavily alloying the nickel with chromium and molybdenum, they form incredibly tenacious, self-healing oxide layers that completely prevent high-temperature oxidation.
And sulfidation too, right?
Yes, they resist sulfidation, which is the highly corrosive, aggressive chemical attack from the sulfur contaminants found in jet fuel.
You know, I like to think of the metal families this way. Aluminum is the lightweight sprinter, perfect for quick, agile movements, mass production, and surviving freezing conditions.
That works.
Titanium is the elite decathlete, incredibly strong, versatile, and light, but very expensive to train and difficult to work with. And nickel is the heavily armored firefighter, wading straight into the roaring flames, taking the absolute worst thermal and chemical punishment imaginable without flinching.
That is a highly accurate and vivid analogy. It perfectly summarizes the metallurgical hierarchy, but it raises a critical design threshold.
Which is,
What happens when we've pushed those metals to their absolute chemical and crystallographic limits? To go even lighter and stiffer than the best aerospace titanium, we can't just hunt for a new metal on the periodic table. We have to fundamentally rethink how matter is woven together.
which brings us to a massive shift in engineering design. Are synthetic fibers the future? What makes composites so fundamentally different from the traditional metals we've spent the last hour discussing?
The single defining characteristic that separates composites from metals is anisotropy.
Anisotropy.
Yes. The metals we've discussed, steel, aluminum, titanium, are generally isotropic. That means their macroscopic material properties like stiffness, yield strength, and thermal expansion are the exact same in every single direction.
So if you pull a block of steel left to right, it resists with the same strength as if you pulled it up and down.
Exactly. Composites, however, are fundamentally anisotropic. Like natural wood, their properties vary vastly depending on the direction of measurement.
Right. A carbon fiber composite is incredibly strong and stiff along the longitudinal axis of the fibers, but it is remarkably weak across them, perpendicular to the fibers.
Which completely changes the designer's job. With metal, I draw the shape of the bracket, and the metal does the rest.
But with composites, the engineer isn't just designing the exterior shape of the part. You have to design the internal architecture of the material itself at the exact same time you design the geometry.
Yes, you have to lay up the plies of carbon fiber in precise orientations, 0 degrees, 45 degrees, 90 degrees, to perfectly match the invisible load paths flowing through the part.
So what does this all mean for how they fail? We spent a massive amount of time talking about how metals fail in fatigue, cracking from cyclic tension. Do composites act the same way?
They behave almost entirely differently, which catches many traditional metal engineers completely off guard. While metals generally fail in tension fatigue, where repeated pulling causes a microscopic flaw to propagate into a fatal crack, composites are often far more susceptible to compression fatigue.
Wait, really? Why compression? I would think pulling on the fibers would snap them.
It comes down to the micromechanics of the two distinct materials working together. In a composite, the incredibly strong carbon or glass fibers provide all the structural strength and stiffness.
Right, the fibers do the heavy lifting.
The polymer matrix, the epoxy resin, is relatively weak. Its only job is to bind the fibers together, transfer the load between them, and hold them in exact alignment.
Okay, so what happens under compression?
Under cyclic compression, those incredibly thin, stiff fibers want to buckle. Imagine pushing down on the ends of a piece of dry spaghetti. The epoxy matrix tries to keep them perfectly straight, but over thousands of compressive cycles, the matrix begins to suffer microcracking, or the bond between the fiber and the epoxy delaminates.
I mean, once the matrix loses its firm grip.
The fibers kink and buckle inward, and the composite suffers a massive, sudden, localized structural collapse.
That is fascinating. It's a completely different failure paradigm. It's an instability failure at the microscopic level rather than a cohesive bond failure.
Exactly. But it's not just strength and weight that make composites valuable. They allow us to perform absolute party tricks with thermal expansion, right?
Ah, tailoring the CTE, the coefficient of thermal expansion.
Yes, and this is a total superpower of composites. Most materials expand when heated. But carbon fibers actually have a slightly negative CTE along their axis, meaning they actually shrink slightly when they get hot.
Shrinking when heated is so counterintuitive.
It is. The epoxy matrix, however, has a high positive CTE. It expands aggressively. By carefully mathematically adjusting the volumetric ratio of fiber to resin and the intricate angles of the fiber layers, an engineer can create a composite part that has a macroscopic CTE of exactly 0.
It will not change size by a single micron, no matter how hot or cold it gets in operation.
Exactly, which is absolutely revolutionary in fields like electronic packaging or space telescopes.
Like in high-power electronics, where the silicon processor chips get incredibly hot, if the circuit board's substrate they are permanently mounted to expands at a different rate than the silicon chip itself, that differential expansion will literally shear and snap the delicate microscopic solder joints connecting them.
Yes, by tailoring the CTE of a composite substrate to perfectly match the thermal expansion of the silicon, you eliminate those thermal stresses entirely.
And we aren't just limited to the standard carbon fiber and epoxy pairings we always hear about, the polymer matrix composites, or PMCs.
No. Advanced engineering utilizes metal matrix composites, or MMCs. You can take a block of aerospace aluminum and intimately infuse it with microscopic silicon carbide ceramic particles.
So combining a metal and a ceramic.
Exactly. It dramatically boosts the specific stiffness and high temperature wear resistance of the aluminum, essentially giving you the ductile toughness of a metal combined with the unyielding rigidity of a ceramic. It's the ultimate blending of material families to defeat specific failure modes.
Okay, so let's pull all of this together. We understand the physical forces of torsion and bending. We understand the failure modes of fatigue, creep, and corrosion. We have a vast palette of materials, from cold-loving aluminum to heat-defying nickel to anisotropic composites.
The toolkit is huge.
The final daunting step of the engineering journey is assembling all these millions of variables into the ultimate optimized design. We can't just build a prototype, break it, add more metal, and try again. We can't rely on blind trial and error anymore.
Exactly. The stakes are too high and the costs are too massive. We use mathematical design optimization. This is where we hand the physics over to the algorithms.
And an optimization model translates the physical world into pure math.
It does, and it has three core components. First, the performance criterion, often called the objective function. This is the one single quantitative thing you are trying to strictly maximize or minimize, like minimizing the total weight of an airplane wing or maximizing the top speed of a race car.
What's the second component?
Second, the independent variables. These are the specific dimensions, thicknesses, or material choices that the engineer or the computer has the power to change during the search.
And the third?
Third, and most importantly, the system model, which consists of the constraints. These are the absolute physics limits that cannot be violated, like ensuring the maximum calculated von Mises stress never exceeds the yield strength, or ensuring the part geometrically fits inside a specific physical envelope.
But engineering in the real world is never that simple, right? The objective function is never just one thing. The boss always walks in and wants it later. AND cheaper, AND stronger, AND manufactured faster.
If we connect this to the bigger picture, it becomes mathematically impossible to optimize for everything simultaneously. You cannot simultaneously minimize material cost, maximize structural reliability, and minimize weight.
They conflict?
They fundamentally mathematically conflict with one another. Improving one degrades the other. To solve this, engineers use a sophisticated technique called goal programming.
Goal programming, how does that work?
Instead of strict optimization of a single variable, you assign preemptive weights and priority factors to your conflicting goals. You are effectively telling the algorithm, Goal 1, avoiding catastrophic failure, is critical. Goal 2, minimizing weight, is highly desirable. And Goal 3, using a cheaper alloy, is just a bonus.
Let me give a very practical, real-world manufacturing example of this conflicting optimization. Think about a CNC lathe in a machine shop cutting a massive titanium part.
Okay, a common scenario.
The shop manager wants to maximize the metal removal rate. They want to spin the part as fast as possible and cut as deep as possible to save time and increase throughput.
Makes perfect sense for business.
But they also want to maximize tool life, because replacing shattered carbide drill bits costs a fortune and halts production. But faster cutting inherently destroys tools faster. How does the optimization algorithm mathematically handle a conflict like that?
The mathematical model uses what we call deviational variables. It sets an idealized perfect target for both the metal removal rate and the tool life.
An impossible target, basically.
Exactly. Then, during the simulation, it measures how far the actual calculated performance deviates from those perfect, impossible targets. The algorithm applies penalties for the underachievement of these specific goals, scaled by the priority weights you assigned.
So it's trying to balance the penalties.
Right. The math navigates the complex trade-off curve, calculating millions of permutations until it finds the precise, optimal cutting speed and feed rate that minimizes the combined penalties.
And because these engineering equations for 3D stress, fluid dynamics, and thermodynamics are highly nonlinear, they curve and exponentialize, like the Paris law we discussed, we have to rely on advanced computer algorithms to do the heavy lifting. We can't solve these with a pencil and paper.
We absolutely cannot. We rely on solvers using algorithms like sequential quadratic programming or FQP. These algorithms are specifically designed to handle highly nonlinear constraints and objective functions.
SQP. That sounds intense.
Imagine the entire design space, every possible combination of lengths, thicknesses, and materials as a massive, multi-dimensional mountain range shrouded in thick fog.
Okay, I'm picturing it.
Every coordinate on the map is a different design iteration.
Yeah.
The elevation of the mountain represents the performance of the part. The SQP algorithm acts like a blindfolded climber dropped into this range.
So it can't see the peak at all?
No, but it feels the local slope of the terrain under its feet using mathematical gradients, and it takes meticulously calculated steps uphill, continually reassessing the slope, to climb to the exact topological peak of performance, all while ensuring it never steps off the cliff of a constraint violation.
It's incredible to think about the journey we've just taken. We've gone from conceptualizing the simple twisting shear of a mathematical shaft, to understanding the microscopic growth of fatigue cracks, to navigating an n-dimensional topographical map with a blindfolded mathematical climber just to find the perfect blend of alloys and geometry.
It's a lot to take in, but it really highlights how deeply the science of mechanical design has evolved.
It is a constant, relentless evolution. We are pushing the absolute limits of known physics, chemistry, and mathematics with every single new generation of machinery, from deep-sea submersibles to orbital spacecraft.
We really are. We're asking more of material than ever before.
And that leads me to a final provocative thought for everyone listening today. We've spent this entire deep dive talking about optimizing static shapes, picking the perfect rigid metal, or weaving the strongest composite fiber. But what if the next massive frontier of engineering isn't static at all?
I like where you're going with this.
Imagine a future of smart, living composites. Materials deliberately embedded with microscopic sensor networks and shape memory alloys that can dynamically alter their own anisotropic properties in real time.
Like an organic system.
Exactly. Imagine a commercial airplane wing that senses a violent turbulent gust, instantly shifts its internal matrix stiffness to redistribute the stress away from a weak point, and then, after the flight, artificially heals its own fatigue microcracks by releasing localized curing agents from embedded microcapsules before the Paris law can ever take hold.
That is exactly the horizon the most advanced materials labs are running toward right now.
It's a total blend of biology and mechanical engineering, taking the concept of survival and optimization down to a cellular level.
A transition from static, dead structures to truly adaptive living machines that respond to their environment just like an organic body.
And building that future all starts with understanding the basic, invisible forces we talked about today. If you got something useful out of today's episode, hit follow and drop a like. It helps grow the show and keeps the engineering knowledge flowing.